Let us now discuss one important application of double integrals. We know that double integrals give us so many physical quantities and geometrical quantities. One such is area of a plane region. Suppose R is a plane region of the xy plane, then it is defined by double integral over the region R of dx dy in Cartesian coordinates, or in polar coordinates it becomes double integral over the region R dr d theta. Let's now utilize this information to work out a couple of problems. Initially, let's discuss the problem. Find the area between the circle x square plus y square is equal to a square and the line x plus y is equal to a in the first quadrant. Here, a is used to denote the radius of the circle, so it will be a positive quantity. So the line x plus y is equal to a passes through a0 and 0a. Therefore, the circle and the line will meet only along the positive direction of x-axis and positive direction of y-axis. We know that x square plus y square is equal to a square is the circle of radius a with the center at origin. So the portion will be as shown in the figure. The first question is how this region is represented in terms of inequalities. There are two ways for us. We can view the region or imagine the region to lie between two horizontal lines and between two vertically oriented curves, or between two vertical lines and between two horizontally oriented curves. Let us take the first category, that means we view the region as the one lying between two horizontal lines. One line is y is equal to 0, another one is y is equal to a. So the limits for y will be 0 less than or equal to y less than or equal to a. Then for x, what is the curve at the left? That is the straight line passing through a0 and 0a. So it can be as well written as x is equal to a minus y. What is the other one? It is a part of the circle lying in the first quadrant or above the x-axis. Therefore, we write it as square root of x is equal to square root of a square minus y square. So, the inequalities for x are a minus y less than or equal to x less than or equal to square root of a square minus y square. When once we know these inequalities, it means we know the limits for the variables. We can easily perform integration and find out the required area. So required area is double integral over the region R dx dy, or it is same as integral y is equal to 0 to a integral x is equal to a minus y to root of a square minus y square dx dy. Let's initially perform integration with respect to x, because x has got variable limits. When you integrate with respect to x, you get x. The limits are a minus y lower limit, root a square minus y square is the upper limit. So, substituting the limits, we get integral y is equal to 0 to a root a square minus y square minus of a minus y dy. We can write it as two separate integrals. The reason is the first of the integrals where root a square minus y square is there can be evaluated easily by using the substitution in terms of sine or cosine functions. The other one can be evaluated directly. So, using the substitution, y is equal to a sin theta in the first integral and root a square minus y square is equal to a cos theta, dy is equal to a cos theta d theta. and then the portion of the circle lies in the first quadrant only, so theta changes from 0 to pi by 2. So now the integral takes the form integral theta is equal to 0 to pi by 2 a square cos square theta d theta plus, now coming to the second integral, integral y dy, that means it becomes y square by 2. Then minus a dy, it becomes minus ay. The limits in the second part are y is equal to 0 and a. So the integral now takes the form integral theta is equal to 0 to pi by 2 a square by 2 into 1 plus cos 2 theta d theta plus a square by 2 minus a square. We notice that here cos square theta is replaced by 1 plus cos 2 theta by 2, and then in the second part we have substituted the limits. Now we can easily perform integration for the first portion to get a square by 2 into theta plus sin 2 theta by 2 to be evaluated at theta is equal to 0 and pi by 2, and then the second part on simplification is minus a square by 2. So further substituting the limits, we get a square by 2 into pi by 2 minus a square by 2 or a square by 4 into pi minus 2. Let's now find out the area of a region or area of the region of the cardioid. So the problem is find by double integration the area of the cardioid r is equal to a into 1 plus cos theta. The cardioid will be as shown in the figure. It consists of two equal portions, or the area of the cardioid consists of two equal portions, one above the x-axis and the other below the x-axis. The portion above the x-axis can be represented in polar coordinates by 0 less than or equal to r less than or equal to a into 1 plus cos theta, and 0 less than or equal to theta less than or equal to pi. Now the required area is written in polar coordinates as 2 times double integral over the region or r dr d theta. Writing the limits, 2 times integral theta is equal to 0 to pi, integral r is equal to 0 to a into 1 plus cos theta r dr d theta. It becomes integral theta is equal to 0 to pi. 2r is now integrated to get r square. The limits are r is equal to 0 and a into 1 plus cos theta d theta. Substituting the limits, we get a square into integral theta is equal to 0 to pi 1 plus cos theta whole square d theta. Now we expand this 1 plus cos theta whole square to get a square into integral theta is equal to 0 to pi 1 plus 2 cos theta plus cos square theta. Again cos square theta is replaced by 1 plus cos 2 theta by 2 and then followed by d theta. Then we integrate to get a square into, we have got 1 plus 1 by 2 in the earlier integral, that becomes a 3 by 2. So 3 by 2 into theta is the integral for it. Integral of 2 cos theta is 2 sin theta. Integral of cos 2 theta by 2 is 1/4 of sin 2 theta. The limits are 0 and pi. On substituting the limits, you get 3 pi a square by